So, welcome back, everyone. It is my great pleasure to announce the keynote talk by Daniel Ferris, who is the Robert Adenbaum Professor for Biomechanics and Neurocontrol, Locomotion and Robotics at the University of Florida. Dan studied mathematics and exercise physiology in Florida. I think it was first the University of Florida, Central University of Florida, and then the University of Miami, before he did his PhD in Berkeley. He has received many honors and awards. Among the very recent awards and honors he has received is the Fellow of the American Institute for Medical and Biological Engineering, the Founders Award of the American Society of Biomechanics in 2018, and the Editor-in-Chief of the IEEE Transactions in Neurosystems and Rehabilitation Engineering. Most of all, Professor Ferris is an incredible beach volleyball player and an enthusiastic and curious scientist, which I most appreciate about him. He is a great person, and I have the honor to know him basically for 15 years. So as long as there is MoBI as the official research field, I know Dan because he spent his sabbatical back in 2008 at the Schwartz Center for Computation and Neuroscience. So I've been working with Scott McCaig on mobile brain-body imaging since 2007. And we've been working on some pointing and other mobile brain-body imaging experiments. And then Dane came, super curious about EEG. He wanted to learn EEG, actually. And then he just hit us in the midst of trying to understand and develop a mobile brain-body imaging approach. And he thought that was a pretty good approach to get a better understanding about gait and biomechanics. So one day he just showed up with a treadmill in his hands and threw that into the lab. And that was the very beginning of a great series of experiments, mobile brain body imaging and treadmill walking, and the very basis and starting point for numerous experiments that followed in the years after. So I'm super happy that he basically was there, and since then he pushed the field. I think mobile brain body imaging wouldn't be at the point where it is right now without him, and without pushing the biomechanical aspects, understanding that not only the neurophysiological basis of gait and gait control, but also technology developments, which I hope we might see during his talks, like the double-layer electrode system to get rid of noise in mobile brain body imaging recordings, the phantom hat for source reconstruction, and many other things. So I'm super curious and looking forward to your talk, Dan, and I'm very happy to have you here. So the stage is all yours.
Thank you very much, Klaus. That was much too kind of an introduction. I do have to say Klaus is correct in that he taught me about EEG way back when, and everything I've learned has come from Klaus. So if you don't like anything I say, please direct your questions to Klaus. Okay, so really what got me into this whole field of MoBI is I used to be an athlete many years ago. I played American football like Klaus, although he played it in Germany. And I'm really astounded at the capabilities of what humans can do. High quality athletes do amazing things with their body. And I'm really curious as to how they control it. And if you approach the question really that the human really is a machine, it's a high functioning robot, how do you analyze what it's doing and figuring out why some individuals outperform others? And in that approach, ever since I started on my PhD in Berkeley many, many years ago, it basically has taken into consideration that you can't just study the biomechanics of human movement, and you can't just study the neuroscience of human movement, and you can't just study the physiology, energetics, metabolics of human movement. All three of them really influence each other quite a lot. A good example is if you try to walk from your home to your car or to a park, you move in a way that minimizes metabolic cost in most instances. And if you're minimizing energy costs, that means you need to control your mechanics with the energetics in mind. And that means your nervous system has to have some sort of sensing and activation of your muscles that work as actuators. And so this approach has worked quite well for us many years in our lab, human neuromechanics lab, first at University of Michigan and now at University of Florida. But I still think we have a long ways to go. It's not just high quality athletes like Usain Bolt, but relatively random humans. Like, you can download this video of somebody who was quite bored during the pandemic quarantine stage where he couldn't get out. And so he kept setting up tasks, this obstacle course for him. And, the capabilities of what the human machine can do are far beyond what we can do with any actual robot right now. And so how do we understand what the nervous system is doing and how it controls the body? I think to do that, you need to make measurements at many different levels. And one of those things that led me to UC San Diego many years ago was to try to figure out what's going on in the brain. If we simplify this down, not thinking of that obstacle course that person just did, but just the neural control of human locomotion, walking and running. What do we know? Well, again, humans and other animals can do remarkable things. You can close your eyes, you can whistle a tune, you can do a lot of things without a whole lot of active involvement. But a great deal of what we've learned about the neural control of locomotion has come from the studying of animals. I had to throw a little Mickey Mouse cartoon in here, as we're not that far from Walt Disney World here in Gainesville. But we need to know more about how humans control locomotion, not just animals. And to do that, we can study peripheral reflexes. We can understand how Hoffman reflexes and 1BA afferents send inhibition or excitation to the muscles through the spinal cord. We can look at patients with spinal cord injury to try to figure out more information about spinal neural networks. But for a long time, we were kind of limited in what we could do to understand the supraspinal areas involved in human locomotor control. From looking at patient populations, we've learned quite a bit, looking at things like transcranial magnetic stimulation, where you can actually excite or inhibit different brain areas. Our understanding of how the brain is involved in controlling locomotion has gotten much more complex throughout the years. I really like this figure from a recent handbook of clinical neurology, because it really does show that it's not just motor cortex, it's not just the sensory cortex. There's an awful lot of brain areas that we have evidence from things like TMS and from patient populations that suggest there's a great deal of cortical and subcortical involvement in the control of locomotion. And so to try to get a better idea of what's really going on in many of these brain areas while humans are actually walking and running, one way to do it is to study using functional magnetic resonance imaging and ask people to lay down and imagine that they're walking. And there's a number of studies out there that have taken that approach. And other people have moved it a little bit further. There are some designs out there where you can actually study pedaling in a MRI magnet. Other people have put this giant cylindrical treadmill while they're in the magnet so that you can actually move your feet in steps. But these are really very limited approach, right? These are basic rhythmic motions. There's a great deal of what really goes on in locomotion that are not included. If you think about what a real world scenario is like, where you're out in natural terrain, or you're in an urban setting where you're having to deal with obstacles like people and other vehicles, trains and bicycles and cars, you are doing much more than just taking repetitive steps or pedaling in a kinematic closed loop chain. So to really understand what's going on in these real world complex whole body movement scenarios, you have to study the brain in these situations. And so one of the things that now allows this is the idea of using high density electroencephalography. So I know this picture has already showed up at least once. This is me doing Klaus's experiment way back in 2007 with our initial biosemi 256, I think we had back then, electrodes. Okay.
I sent you a picture of me with the same, so you can use that for your talk.
Thank you. And we've come a long way since 2007. And Klaus is completely right. I went and did a sabbatical. I knew very little about EEG then. And this is what Klaus looked like way back when, for those that didn't get a chance to see him. He was a little bit younger then. I think we all were. Scott McCaig was the director of the lab at the Schwartz Center for Computational Neuroscience. And I was very curious as to try to understand what the brain was doing in locomotion. I actually did go out to, I actually went to the local mall after the first day of data collections, and I was frustrated by the fact that with the small room we were in, people kept having to turn and step over things. And I really wanted to just simplify it to just pretty basic long-term walking. And so I went and I bought a treadmill at the mall, put it in my wife's car because it would fit, took it to the lab at about 11:30 at night, set it up, and the next morning for the second day of data collections, Klaus and Scott were a little surprised to see a treadmill in the middle of their lab. But that's really how we started taking EEG to actual treadmill locomotion. They made me aware of what EEG lab was and trained me in a lot of aspects. Although now, to tell you the truth, I don't use it at all. I don't think I've used EEG lab myself in at least 10 years, because as you become a professor, you grow and you have a lot of grad students and postdocs and research scientists, and a lot of people do the actual work, and you sit there and have meetings all day. But it's a great tool. And yes, as Klaus commented, there was a little bit of bias on my part why I chose Scott and Klaus and UC San Diego's, because if you've ever been there, they have great beach volleyball. I highly recommend going if you go visit next year for the MoBI meeting. Okay, so one thing I sort of want to highlight is there are an awful lot of algorithms and software approaches to trying to do signal processing for EEG and MoBI. In many cases, you want to remove eye artifacts or muscle artifacts, motion artifacts, and there's lots of different ways. No one way is best, and that really needs to come through. The reason that we can't tell you, oh, this one is superior than all others for your data analysis really comes down to what type of data you have, how much motion artifact you have relative to brain activity, how much eye or muscle artifact. Is your muscle artifact rhythmic, or is your muscle artifact discrete? Is it very high amplitude or low amplitude relative to the eye? What type of motion artifact? Is the motion artifact you have coupled to the brain activity that you care about, or are you looking at something in the brain activity that is fundamentally non-coupled to your motion artifact? All of these things make your data sets unique relative to what other people are studying. There's this really nice paper I would recommend taking a look at that looked at how different types of signal processing approaches for EEG, how well they work. And their take-home message really is it depends on what your data look like. How much motion artifact, how much muscle, is it discrete, is it rhythmic? All of those things that make your data unique really influence which of the signal processing approaches really are best for your data. So unfortunately, it makes it a little bit more of an art form than it is a straight up, oh, we have created this one approach and just use this one pipeline and it's perfect. In EEG, MoBI, at least right now, there's a lot of different tools in the toolbox, and you need to sort of convince yourself that the tool you're using works best. And to put this in perspective, as a parent of a teenager, this is my daughter, Jasmine. I know Klaus understands this as well, since he has a teenage child as well. The idea of what is clean and what is not clean is highly variable. When my daughter tells me, yes, her room is clean, and I take a picture, this is literally from 30 minutes ago, what I think of as clean and what she thinks of as clean are two different things. And so the same is holding true for your data. You're not going to get a discrete clean and not clean. There's going to be some range in between. It is really shades of black and white where there's a lot of gray, and you need to figure out what you need to, how clean is clean enough for you to interpret your data. The approach that we take in my lab is based off of teachings from Scott and Klaas, really use independent component analysis as our main tool. And you've heard a lot about ICA. A lot of times people relate it to solving the classic cocktail party problem, where if there are lots of people talking in a big room, it's really hard to distinguish one voice from all of them. But ICA is really good as a blind source separation technique for pulling out individual voices from many, many. One way to think about it is imagine that you have 4 areas in your brain that are highly active. And when I say areas, I don't mean 1 neuron, 10 neurons. I mean thousands of neurons that are changing their membrane potentials in synchrony. And when you have these 4 areas and you put 4 electrodes on the scalp over those brain areas, you're actually going to record in each of those EEG sensors from all of those brain areas underneath. And so anytime you look at a sensor level analysis, if they're looking at a channel of EEG and they use signal processing to analyze it, you really don't know what brain area underneath there is what you're getting, because they're all going to mix together as far field potentials. And so what ICA allows you to do is it creates an unmixing matrix that hopefully, in an ideal world, separates out the individual sources that originally came from different brain areas. So this is what it looks like. If you start with a subject and you have 256 electrodes on their head, and then let's say that 33 of the channels were kind of noisy and didn't have good connections, so you get rid of them. You have 223 clean or relatively clean channels of EEG. You run it through an unmixing matrix. You are going to get 223 sources of the electrical activity that shows up in those channels. Because of the square nature of the unmixing matrix, you will get ICs or independent components for every channel that you start out with. And then with an inverse head model, you can actually look for where the source is and create an equivalent dipole that's generating the electrical far field potential that is picked up at the channel level. And so you end up with a mix of this. You have a lot of different brain areas from a given subject. And so what do you do then? As we just heard, there are a lot of tools for actually doing clustering and trying to put together some of these different clusters. When we started doing this, Joe Gwynn was a PhD student of mine, and we would look at the data and we would say, well, does this physiologically make sense where we're getting these independent components and these equivalent dipoles? And here are 3 locations of a given subject shown here in the red and the green and the blue in a 3D map of a head. And then these are the topo plots. So these are looking at how independent component 2 is affecting electrodes that are put around the head. Here's the nose, here's the ears. You can see that it's affecting electrodes at the back of the head very differently than it would affect electrodes or at the front of the head. And you can do this for all of your independent components to look at the topo plots. And you can see some sort of groupings. It looks like these are very much affecting electrodes at the front of the head, more so than IC11. And in fact, when you look at the time series that's pulled out in the independent component analysis, you can actually say and correlate it to things like vertical eye movement or horizontal eye movement. There are changes in the electrical potentials of those ICs. And lo and behold, it looks like from the inverse head model that the source localization puts them right in the eye socket. And then there's other independent components that we saw, things like this, which is a repetitive change in electrical potential. And it turns out this matches up really well with the heartbeat because it's the electrocardiography. In other words, the electrical potential of the heart propagates as a far field potential all the way up and is picked up by EEG electrodes in some cases. It doesn't have a map all the way down to the torso and the heart. So where does it put the equivalent electrical dipole? It pushes it to the edge of the map. It can't calculate the true origin source localization. So it basically pushes out towards the edge and says it's somewhere where I can't calculate. We would also see things like other ICs that would show up as locations right at the back of the head in the neck region. And it actually turned out these were good representations of the EMG. If you put EMG electrodes on the neck and record the neck muscle activity, these correlate, independent components correlate quite well with neck muscle EMG, because the magnitude of EMG in the neck muscles is usually much higher than a lot of the brain areas. And so it's going to propagate a little bit further. It's going to show up, and you need to remove it with independent component analysis or other approaches. So here's a video of some of our first original papers. Klaus and Joe and Scott McCaig and I published a couple of papers in 2010 where we looked at subjects walking and running on our treadmill in Michigan, and we showed them little X's and pluses, and we tried to decipher a visual oddball task. And this is where we started, and we thought this was an amazing achievement for us. But lo and behold, when I went out to conferences, I got a lot of non-believers, the people that really thought what we were getting was just motion artifact. It really didn't represent real brain areas. And there were a lot of skeptics. And that's fine. I'm a big believer that you need to listen to your skeptics in science. Don't just assume your theories and your approaches are valid. If they don't believe something, ask yourself why, and how can you prove that what you're doing is wrong, in line with what they think. And so over the years, we've developed a number of electrical head phantoms. These are essentially electronic brains embedded within either dental plaster or ballistics gel mixed with salt, where we can control the underlying brain signals. So if we're broadcasting a known ground truth, and then we put EEG systems on over the top and record, we can look at how well our signal processing approaches actually pull out the underlying brain sources that we're broadcasting. And right now, we've gone through a number of papers. You're welcome to take a look at these over the years in some of the ways that we've tried to quantify and convince ourselves that maybe what our signal processing approach is doing is valid. One thing that I'll point out that is a recent study by Stephen Peterson, a grad student in my lab, was really nice, is that he took one of the dental plaster phantoms and he broadcast different electrical signals that he actually generated with a neuronal mass model. So here are different antennae within the head phantom, and he used a neuronal mass model to create connectivity between different brain areas. And he looked at different frequency ranges using simple signals that were in low, middle, and high frequency ranges. So here's the spectral power breakdown of the signals that we were broadcasting for relatively simple signals. And then he did it again for a little bit more complex signals. You can see the time series here versus the potential that was being broadcast of different signals. And then here's the spectral power breakdown of what was being broadcast in these different areas. But using the neuronal mass model, he was able to actually build in real connectivity between different brain areas so that we know they were affecting each other. And in doing so, what his main goal was he wanted to test different connectivity measures. There are a lot of different ways to measure brain connectivity with EEG. Here are 1, 2, 3, 4, 5, 6, 7 of them that he has tested with the phantom. And we were really worried that having motion artifact in the head phantom would show up as spurious positive or false positives. It would suggest that brain areas were connected simply because they had similar motion artifacts. And I'm not going to go into the long details. You're welcome to take a look at the paper if you want. But it was true. There were a lot of these that worked to find the real connectivity, but they also found a lot of false positives. And in fact, the directed the directed transfer function, DDTF, was the best one that we used, that we found for our phantom experiments. It had the fewest number of false positives. It really only found connectivity when there was real connectivity. And so in a number of other studies that he went on to do, we use that as a way to look at, with mobile brain imaging, looking at brain connectivity while people are walking and doing challenging balance tasks. Our head phantom has gotten more complex over the years. Natalie Richet, Ryan Downey have worked on some aspects in the lab, and they've, in collaboration based off of some of the advancements that Dave Hairston at the Army Research Lab has made, figured out ways to make our phantoms a little bit more well-controlled and more complicated, where we can have neck and eye broadcasting for electrical potentials, along with multiple sources, and we can control from one phantom to the next really well what's going on in the inner workings of our electrical brain. They did some really cool work, and in fact, they got a little, this phantom they were calling Gary. That's why the Gary is up there. It just sort of reflects the next generation we've gotten to. And I have to give credit to Ryan and Natalie for their Harry Gary versions. So we've tried a number of different wigs and putting the EEG systems over so that we can make measurements and actually figure out, you know, how much is the hair affecting our recordings, and does it make the motion artifact worse when you have hair? And so I'm not going to go into a whole lot of detail. There are going to be some more interesting papers coming out in the future, hopefully on this, as we continue to develop the head phantom and make Harry Gary even more complex. One of the approaches we've taken over the years was really dual EEG electrode design. So Andrew Norden was a postdoc and research scientist in my lab for a number of years. He's now at Texas A&M. And this was one of the projects he worked on for with ARL funding. But essentially, the normal procedure for measuring EEGs, you have here, this red is a normal EEG electrode that has conductive gel between it and the scalp. But what we've done is taken a second EEG electrode, invert it, mechanically couple it to the first EEG electrode, but electrically isolate it from the first EEG electrode. So in doing so, we would take this conductive fabric, carbon-infused cloth, over the top that acted as an artificial skin. So as this first electrode was moved around in motion to create motion artifact, the second electrode gets the same type of motion artifact because it's moving with the first electrode. So we get a really good measure of what motion artifact looks like without getting any of the brain signals or the eye or the muscle signals. And this makes it easier to pull out what's really going on. Here's one of our phantom heads on a motion platform that's moving up and down. We had taken an IMU and put it on humans as they walk, recorded how their head actually moves while they're walking at a brisk pace, and then we played it back for our head phantom. And then with this dual electrode setup, here are an example of what 8 different EEG channels would look like versus time. And you can see that there's a fair bit of motion artifact from just visually inspecting the signals. But when we're actually going through, we can take the motion artifact out because we have a good representation of it, and we get a much cleaner signal of what the first electrode is just measuring from the underlying brain signals. There's a couple of papers in Journal of Neural Engineering and Scientific Reports that talk about this approach. And in fact, when we looked and made quantitative metrics of how well we were pulling out original phantom sources, we were getting cross correlations greater than 0.9 for all of our analysis, which suggests to ourselves and to many others that what we're doing actually may be working. And so over the years, we've progressed. This is a paper I'll talk about in a little bit, where we looked at subjects running and walking on a treadmill and stepping over obstacles that we threw on their way. And you know, in the time point of those 10 years, going from 2000 to 2010 to 2019, I think we finally convinced enough people that our approach has validity, and that, okay, you know what, I'll believe what you have to say. I think there's a large enough, you know, series of papers, 25, 30 papers now out of our lab that have looked at the validity of the methods. And trying to show that the brain dynamics are actually being represented in this MoBI approach. So what can you do with it? Again, I was an athlete growing up, and I grew up in Orlando. So I was really happy in the early Shaquille O'Neal years when he was playing basketball for the Orlando Magic. But he's no longer playing basketball. And it turns out as Shaquille ages and the rest of us age, falls are much more common. This is not unique. Shaquille used to be arguably, one of the best athletes in the world. And now you can search Google for lots of examples of him falling down on TV. Why is that? Is it a problem with his muscles? Is it a problem that he can't produce the biomechanical response necessary to keep himself upright? Or is the problem really in control? Is he not being able to activate the muscles in the way he should? Or is it sensing? Does he know when he's starting to lose his balance and he can respond? Is that the problem? To get at that question, that's a perfect idea or a perfect area of research for MoBI. Turns out IRB human protection boards don't like it when you're telling them you're studying people falling down. So we had to come up with a way to study people falling down but being safe. And what we came up with is walking on a small balance beam on a treadmill. And in doing so, we know exactly when they lose their balance because they step off the balance beam. But there's very little chance of them getting harmed because they're stepping 1 inch off onto the treadmill. With doing this, we actually wanted to know what parts of your brain seem to care about you losing balance, which ones respond first, and maybe later on, we'd love to be able to study older subjects that have a higher propensity for falling and find out, is it a matter of sensing or is it a matter of control? Or is it a matter of mechanics that leads them to have greater number of falls? So Amy Sipe, who was a postdoc in the lab, looked at 20 subjects walking on a balance beam. Up top are independent components that have been clustered together into different brain areas based on their spectral properties and their locations and the weighting matrix that we put together. Here down below are the mean locations of each of the clusters. And the first thing that I would highlight is that there's a lot of your brain that seems to care about you losing balance. It's not just sensory motor cortex, but a lot of different areas are involved in this calculation. And if you look at which area goes first, it turns out the left sensory motor cortex in our subjects, who were all right-footed, in case you're wondering, had the earliest signal that they were losing balance. So on the x-axis is time, and the BCs are beam contact when the foot hits the balance beam, and then the TC is a treadmill contact. So when you see the first TC vertical line, what you're seeing is when they put their foot on the treadmill after they've lost balance. On the y-axis is the frequency in this ERSP, the event-related spectral perturbation graph. It's broken down into theta and alpha and beta regions and gamma. And when we look at what brain area comes up, there's a large theta and a little bit of alpha spectral power that comes up, delta. And you'll notice that it comes actually about a second before you actually step off the balance beam. And it is triggered by putting the leading foot on the balance beam. And so at this point where this vertical line is, what you see is that you have both feet on the ground. And having 2 feet on the balance beam is really important because it gives you 2 ways to calculate where your center of mass is and calculate your center of mass velocity. Rather than relying on 1 leg's worth of noisy signals, you have 2 feet on the ground, which make for much higher reliability of your calculations. Over the years, we've taken this approach and expanded it a little bit further. Stephen Peterson was a grad student in the lab who was really curious about different ways to improve balance. When you look at physical therapy and their approaches to improving balance, there are 2 sort of big approaches that a lot of therapists go by. One of them is to give them physical perturbations. In other words, you push or pull them while they're walking or they're doing a balance task. so that they have to learn how to balance better. Another approach is not to push or pull them with physical forces, but to give them visual perturbations. You can take away their vision, or you can tilt their vision, which is exactly what Steven Peterson did. In this case, he gave him a Oculus headset for virtual reality, put a little camera on the front so they saw the real world, but he was able to actually induce artificial rotations in their vision when he wanted to. And what he wanted to know is, okay, we have physical therapy that likes these two different types of perturbations. Do they really affect the brain similarly, or are they really acting on two different brain areas? And so he took 30 subjects walking on the balance beam while they underwent visual and physical perturbations. Up top are, again, the independent components from the individual subjects that have been clustered together to get the mean locations down below. Again, shouldn't be a surprise that there's a lot of different brain areas that seem to be involved in maintaining balance while you're walking. And now I'm going to show you ERSs from 8 different brain areas. So we have occipital up here on the top left, posterior parietal and anterior parietal down here on the bottom left, left sensory motor, right sensory motor, supplementary motor, and anterior cingulate. The anterior cingulate is an area of your brain that's very involved in error monitoring. That's been shown for lots of different cognitive tests that it's very responsive in terms of synchronization or an ERP or an event-related potential in regards to monitoring errors. And again, on the x-axis, we have the time. Our vertical bars that you see in dashed lines are when the perturbation starts and when the perturbation ends after half a second. And so what you see is that, number one, we were expecting occipital changes in spectral power, and that was very clear. When you perturb somebody's vision, occipital brain area responds with this very strong theta and a little bit of alpha synchronization, followed by a alpha beta desynchronization. And you'll notice that the response from the initial perturbation is sort of mirrored, again, a little bit less strongly after you restore vision. So your brain is responding very similarly to the perturbation, to the removal of the perturbation. And there was very little response in anterior cingulate or the sensory motor cortex or supplementary motor, but you had a very strong response in the posterior parietal cortex with the visual perturbation. The posterior parietal cortex is an area that's involved in integration of many different sensory streams. So things like vestibular, proprioceptive, visual, inflow all come into posterior parietal cortex for sort of calculating your body position and where you are in real world space. So, you know, it was actually very encouraging to see that visual perturbations produced a very strong brain response in the posterior parietal cortex. Compare that response to the physical perturbations. So number one, occipital had very little response. You're not giving them a visual perturbation. But posterior parietal cortex actually didn't have a very strong response to a physical perturbation. It was less about integrating different types of sensory information and more so about very strong responses in sensory motor cortex and the supplementary motor area, and a little bit of anterior cingulate and anterior parietal. So, you know, if you look at the very different responses, these 5 brain areas have a strong response with physical perturbations, and these 3 brain areas have a very different strong response to visual perturbations. I would say the take-home message from this is that not all interventions for improving balance are going to affect individuals the same, is that you're going to target different brain areas for producing responses. And so if you have somebody who their underlying problem is in the supplementary motor area or sensory motor cortex, then maybe physical perturbations are going to be the better area to target. On the other hand, if the integration of sensory information is the primary problem in controlling balance, maybe visual perturbations would be the best for intervention. Okay, so in the real world, it's not uncommon for you to see obstacles that you have to encounter. It could even be things like stepping stones for foot placement, If you're in an urban setting after a rain, you would have to step over an obstacle like a puddle. Small children do this regularly playing hopscotch. And if you're a little more daring, there are other ways that you can challenge your ability to step over obstacles. Here's a really nice example of a person leaping a very fast car. And thinking about what needs to go on in these brain processes of what you're doing. It's an integration of the visual information with your body proprioceptive sense and trying to time your muscle activations to step over the obstacle. There's been a lot of really good work by Trevor Drew and colleagues. Dan Marigold published this paper that I'm taking some of the figures from, where they've looked at cats and they've actually made indwelling brain recordings from the cats. And when you do this, one of the areas that they've highlighted that seems to be super important in the calculations is the posterior parietal cortex. And that it shows an increasing response in terms of the number of spikes per second as you get very close to the obstacle. And then it quickly declines as you go over the obstacle. With this in mind, they've sort of put together this framework about how the posterior parietal cortex integrates information from lots of different sensory inflows and is used for sort of planning timing when you're stepping over the obstacle. So given this large data set on cats in terms of the importance of posterior parietal cortex, one of our quick questions was really, can we find evidence of posterior parietal cortex involvement with stepping over obstacles? So Andrew Norden did this really elegant series of data collections where we had subjects walk and run while we put this little obstacle underneath a visual blind and that they saw and they had to react to and get over. And when we look at the event-related spectral perturbation, I'm going to show you examples like this, what is broken down with different vertical lines that are synchronized to when the obstacle first appears, to when the obstacle is directly underneath them, and then when the obstacle goes off the treadmill. And in doing so, we can find actually multiple brain areas that show very strong synchronizations to appearance of the device or stepping over it. So in this particular case, here's premotor cortex cluster at different walking speeds of 0.5 meters per second, which is a pretty slow walk, to brisk walks of 1.5 and 2 meters per second, going at the same speed, but running with an aerial phase and going to a little bit faster run. You'll see that qualitatively, the signal response in the premotor cortex is very similar. It looks like the response is getting longer in duration, but it's really not getting longer in duration. It's that this time from the first vertical line to the second vertical line is getting much shorter. And because we're stretching it out so that it has the same distance on the graph, it looks like that the activation is becoming longer in duration, but it's about the same duration. It's a very strong spectral response of synchronization in alpha, theta, even a little beta in some cases. But the signal quality was maintained for a range of different walking and running speeds. Really interestingly, when we tested the idea of posterior parietal cortex activation versus motor cortex and premotor cortex, we found very big differences in when the activation started. So here on the y-axis is the activation onset of the synchronization that I showed you at different walking speeds here, 0.5, 1.0, 1.5, 2.0. And you'll notice that the brain area that responds the soonest to when the object appears is actually premotor and primary motor cortex. Very quickly, within 100 to 150 milliseconds, you're showing a strong synchronization. The posterior parietal cortex doesn't show the strong synchronization immediately when the object appears. It actually times itself to the penultimate step. So you're right about to step over. So it's so slow speeds when you have many steps between where the object appears and when you actually go over it, to when object is moving very quickly and you only have one quick step. the timing of the posterior parietal cortex is synchronization is modified so that it occurs right as the step before you go off the obstacle. So which actually mirrors the data from Trevor Drew quite well. Okay, so the types of algorithms that we use to clean up our data are getting better all the time. I want to highlight some of the recent work by Ryan Downey, a research scientist in our lab, in his new algorithm called I Can Clean. You've already heard about our dual electrode setup, right? We have one electrode that's measuring normal EEG. We physically couple the second noise electrode, put an artificial scalp over the top, and then we can get signals from both of them. You can do a one-to-one match so that every electrode is actually both an EEG cortical electrode and a noise electrode. But over the years, we figured out that actually maybe you don't need to do a one-to-one match. Maybe a 1-to-3 match is sufficient. So only 1 out of every 3 EEG electrodes actually has a noise electrode, because the noise recorded in one place actually is quite similar to the noise from the surrounding electrodes. So it's a good way to reduce the weight and the scope, the scale of all the electrodes you're putting on your subjects. But what Ryan has figured out is that canonical correlation analysis, CCA, can produce some really nice filtering when you have these noise electrodes in the system. And essentially the way CCA is working is it's trying to find maximum correlation between aspects of your EEG data and your pure noise signals. I'm not going to go into the specifics. Ryan's online. If you have questions, feel free to direct them to him after I finish. But the results are actually quite impressive. So here's an example of some raw EEG channels from a subject walking on a treadmill with some uneven terrain. And using the I Can Clean algorithm, he's able to pull out the noise components, project it onto the EEG, look at some of the raw noise from the motion artifact that's being recorded in the dual electrodes, and then basically try to clean up the EEG. And again, remember the statement about my daughter's room, clean is relative. So would I rather work with these channel signals than these channel signals? Absolutely. Is it perfectly clean? Probably not. There's still probably a little bit of motion or muscle or eye artifacts that's left in this, but it's a much better starting point than where you are from the raw EEG. And so one of the reasons we started down this road is we're studying young and older subjects walking on different types of uneven terrain. We came up with a nice way to vary the level of the unevenness of the terrain. We basically have hard foam pucks that we Velcro to the surface, and we can quickly change it in and out. So by changing the height of each individual puck, along with the relative variability of the height of the pucks, but putting them in exactly the same positions over and over again, we can actually look at how your brain is responding to being on more uneven surfaces where it's more challenging to your stability. One of the other projects that we started not too long ago is in collaboration with Professor Rachel Seidler, who's actually my wife at the University of Florida, who is a tennis player. And we were really curious to try to figure out if we could get your brain dynamics while you're playing tennis. So we know we've done a decent job with treadmill walking and running, but treadmill walking and running, you're moving in a stereotypical fashion in one sort of main direction. When you play tennis, you accelerate, you slow down, you move left, you move right, you move forward, you move back. There's twisting of the torso, there's motion of the head. There's a lot more challenging scenario than just constant speed running on a treadmill. And so we started looking at how to use our dual EEG system in a portable setup, started collecting some nice data, and you don't see many people sort of highlight their failures, but we have sort of abandoned for the immediate future trying to measure tennis. The amount of motion artifact and muscle artifact has been really difficult to overcome. I would love to be able to say that we can get reliable brain dynamics out of playing tennis in all of our subjects. I would say out of the 10 or so subjects we recorded, roughly, maybe we've got good brain dynamics for 1 or 2. It's a really hard problem. I think, a lot of the motion of the head separate from the torso, where you turn your head left and right and up and down, puts a lot of strain on the cords, the wires that are going down to your amplifiers. So we've looked at this a different way. We've said, how can we take the same general task and try to understand the basic same scientific questions, but in a situation with less motion? And we've moved to table tennis. So this is work of Amanda Studnicki, who's online now for her dissertation. We've got subjects that are outfitted with our dual EEG setup while they're playing not only against a human, but also against a table tennis machine that's feeding them balls. And we have IMUs on the paddle and on the net so that we can record when they hit the net and make an error, when they hit with the paddle. And what we're looking for is, honestly, the overriding question is, if the posterior parietal cortex is very involved in timing of your body to an obstacle, what about to interception of a moving ball? You're trying to use your paddle to intercept the ball. Do we show clear timing of an earth spectral power sort of theta alpha synchronization in regards to making contact with the ball? And so Amanda is in the middle of her data collections right now. I think she's somewhere on the order of 10 subjects. She's making good progress. Hope to show results of this next year at the MoBI conference. We know there's a lot of companies out there that are making progress at trying to develop lower number of channel mobile systems. There are lots of reasons to do this. One of them is basic science research, but I don't think that's what's driving a lot of them. There's neuromarketing research where you can actually study humans in real situations, like moving through a supermarket and trying to figure out how they react to product placement or the design of the store. There's also people that are very driven by making this work for interactive video games. So whether it be virtual reality or playing video games at home, can you actually couple your brain dynamics to the game so it knows when you're bored, or it knows when you're overstimulated, or knows when you find the task too difficult? There are lots of reasons why having mobile EEG systems plugged into your video game or your entertainment sort of experience would be valuable. From a basic science standpoint, there's a lot with brain injury that we don't understand. Being able to use sort of wearable systems that you could actually mount inside of an American football helmet would be amazing. You could actually look at how their brain dynamics change right after an impact with their head. For looking at things like old age, strokes, doing rehabilitation, trying to understand the processes that are ongoing in their brain would be very helpful. There are some people that want to use EEG signals as one way to decipher the intent of users of exoskeletons. Yes, I'll go back to beach volleyball. I would love to be able to actually study people playing very complicated sports, try to understand their brain as to how they're focusing on the many tasks that they have to deal with, where the ball is, where the opponents are, how they're deciding to choose the motor actions that they are. And you could actually throw in virtual reality. There's a lot of people out there in the business world that would like to use virtual reality to train American football players, to get them better situated so that you don't have to have practices with 20 people for 3 or 4 hours. If you can do them in the off season and have them use virtual reality, what sort of information can we get out of their brain in these virtual reality settings? And then, I touched a little bit on brain-computer interfaces, but this is a typical EEG brain-computer interface right now. A subject sitting down, looking at a computer screen, trying to get a cursor to move. I would love to take BCIs out of the lab and have them work in the real world. And there's lots of different reasons for it. One of them would be to actually allow a little bit more complicated mobile exoskeleton system. So if you know a little bit about Iron Man, you'll know that in his helmet, he actually has what amounts to an EEG system that records and interacts with his electrical cortical signals that allows him to control various things. Can we get to that point where we're using these more complicated EEG systems to interact with prostheses or exoskeletons? I think it's possible that we can get to more complicated systems. And these techniques that we're working on for MoBI are going to be necessary if these brain-computer interfaces are ever going to be mobile. So thank you very much for listening. I got to give credit to an awful lot of people that have helped over the years, and I'm sure there's people I'm leaving out here. I tried to highlight them in some of the talks along the way, but here are some other people that in some cases I didn't highlight.